Okay, so let's take a look at another equation. This time, let's take a look at what happens when water, okay, and let me rewrite water so we can study this reaction a little bit. Here's our water molecule, so let me draw it as a Lewis structure. Let's say a water molecule reacts with another water molecule, okay? So in the way this would happen is that the O from one of the waters is going to pull the hydrogen from one water. We break that OH bond, and that pair of electrons goes over the other oxygen. So in this kind of a reaction, which also happens at equilibrium, one product is going to be H3O plus, okay? And then the other product is going to be OH minus. All right, so this is an equilibrium reaction. And if we were to write the Kc expression for this reaction, it would be the concentration of H3O plus times the concentration of OH minus divided by the concentration of water. Now, since you have water you have 2 moles of water, this is really just going to be water squared. Okay. Now, here is a thing though. Water is going to be usually liquid, and then H3O plus and OH minus are going to be aqueous. So we can't have a reaction that has, heterogeneous layers, or, water is definitely has the concentration of water is not changing. The concentration of water is about 55.4 molar. So that means we have to rewrite this expression. We have to write this equilibrium expression. Basically, we end up multiplying the concentration of water squared by both sides, so that way it gets out of the denominator. So we're going to be left with this. The right-hand side of the equation turns into the concentration of H3O plus times the concentration of OH minus. And this is equal to a new equilibrium constant. We're going to call this Kw. This is a really special reaction, and this actually has a value. So that value, and I apologize that this chart is in the middle of the note, so I apologize. That really shouldn't be there. So let me rewrite over. I'm going to write over this. Hopefully you can see it. But the Kw, the equilibrium constant for this reaction, is going to be 1.0 times 10 to the minus 14th. Okay, and we call this number the ion product constant for water. Okay, now what can we say? What can we say about the concentration of hydroxide ion versus the concentration of H2O plus in pure water? Well, in pure water, okay, the pH should be 7. So the concentration of acid should be equal to the concentration of base. Okay. Now, what variable is going to cause a change in this new equilibrium constant Kw? Just like we talked about in the last chapter, temperature. Okay. Now, experimentally, in pure water at 25 degrees Celsius, the concentration of H3O plus is going to be 1.0 times 10 to the minus 7th molar. And so the concentration of hydroxide ion should be 1.0 times 10 to the minus 7th molar, because they're going to be equal to each other if this is pure water. So that means that the Kw should be the concentration of the base, 1.0 times 10 to the minus 7th molar, times the concentration of the acid, 1.0 times 10 to the minus 7th molar. And that should give you, those two values together should be 1.0 times 10 to the minus 14th. Okay, and so that's how we're getting that equilibrium constant. Now, keep in mind that if we talk about an acidic solution means that the concentration of H3O plus is going to be greater than the concentration of OH minus. Okay. So that's the acidic solution. The concentration of H3O plus is going to be greater than the concentration of OH minus. A basic solution means that the concentration of OH minus is going to be greater than the concentration of H3O plus. And if it's neutral, then both concentrations will be equal to each other. So the concentration of OH minus is going to be equal to the concentration of H3O plus. All right. So what's really nice is that we've got an equation to figure out the equilibrium. If you know either the concentration of H3O plus or the concentration of OH minus, you can always solve for the other. So let's try this out. So if you know the concentration of H3O plus is 0.0010 molar, or 1.0 times 10 to the minus third, we can solve for the concentration of OH minus. So let me write that equilibrium expression again. So Kw is equal to the concentration of H3O plus times the concentration of OH minus. If I solve for the concentration of OH minus, I've got to divide both sides by H3O plus. So I get this, that the concentration of OH minus is going to be equal to Kw divided by the concentration of H3O plus. Okay, so Kw is a constant. That doesn't change as long as the temperature stays the same. 1.0 times 10 to the minus 14th divided by the concentration of H3O plus. This is case, it's 1.0 times 10 to the minus third molar. So this together should give us 1.0 times 10 to the minus 11th. Let me rewrite that a little bit clearer. I'm going to write that right over here. 1.0 times 10 to the minus 11th molar. Okay. And so if we know one, using Kw, we can find the other. Let's try it the other way. What if the concentration of OH minus is 1.0 times 10 to the minus third? We would use the same equilibrium equation. Kw is equal to the concentration of H3O plus times the concentration of OH minus. This time we're going to solve for H3O plus, so we're going to divide both sides by OH minus. So that means that concentration of H3O plus is going to be equal to the concentration, it's going to be equal to Kw divided by the concentration of OH minus. Or 1.0 times 10 to the negative 14th divided by 1.0 times 10 to the minus third. And that means that the concentration of OH minus should be 1.0 times 10 to the minus 11th molar. So it's kind of nice. If you've got one, you're missing the, if you're missing one, you can definitely find it. And then this figure is really just correlating with what we talked about up here, that the concentration in an acidic solution, you're going to have more H3O plus than OH minus. Basic solution, you're going to have more OH minus than H3O plus. And if it's neutral, they're going to be equal to each other. All right, so that's all well and good. We can work with concentrations. It does get a little tedious, especially when we're dealing with numbers as small as 10 to the minus 11th. So we do have a scale that helps us out, and this is going to be based on the logarithmic scale. THMIC scale. Okay, so the way that we're going to define the scale is called the pH scale, or powers of hydrogen. And so the way it works is that the powers of hydrogen, pH, is going to be equal to the negative log of the concentration of H3O plus. Okay, and so on the scale, as long as the pH is below 7, then we say that it's an acidic solution. If the pH is above 7, it's basic, and pH is 7, we know it's neutral. Okay, now we can also turn around and find the concentration of H3O plus. Okay, so let's say instead of solving for pH, you had to solve for H3O plus. What that equation would look like is this. We have to undo that logarithm. So we would say that we would take the concentration of H3O plus. This is going to be equal to the power of 10 raised to the negative pH. Okay, and so here's our first question. Find the pH of a 0.060 molar H3O plus solution. Okay, so the way this works, we use our equation. pH is equal to the negative log of the concentration of H3O plus. And then we take the negative log of our value, 0.060 molar. If we take the negative log of 0.060, the pH is going to be 1.22, so this is going to be very acidic. Okay. Now, if we wanted to find the pH of, let's say the concentration is 0.060 molar hydroxide ion, we've got to find the concentration of H3O plus. So this is going to be a two-parter for us. First, we have to find the concentration of H3O plus using the equilibrium expression. Okay, so Kw is equal to the concentration of H3O plus times the concentration of OH minus. Okay, we're going to divide both sides by OH, so that way we get H3O plus by itself. So the concentration of H3O plus is equal to Kw divided by OH minus. Okay, or 1.0 times 10 to the minus 14th divided by the concentration of OH minus, which is 0.060. So that concentration of H3O plus should be 1.7 times 10 to the minus 13th. And then based on this, we could take the pH is equal to the negative log of the concentration of H3O plus, which we just found was this value. So if we plug it in, the pH would be equal to 12.78, which this is definitely a basic solution. Okay. Now, we could also find something called POH. So not only do you have powers of hydrogen, you have powers of hydroxide as well. And so if you know the concentration of hydroxide ion, and you take the negative log of that value as well, that's going to give you POH. Okay. And if you need to find the concentration of hydroxide ion, that would be 10 raised to the negative POH as well. Now, there is a relationship between pH and POH. If you take pH and you add the POH to it, these two values must add up to 14. So everything's all related to each other. Okay. All right, so if we were to find the POH of that second solution, we know what the pH is, which was 12.78. POH, if we subtract 14 from 12.78, that's going to leave us with 1.22. And so if we want to backtrack, actually we just found the POH of this reaction. But if we wanted to find out what the concentration of hydroxide ion, all we have to do is take 10 raised to the negative POH, which is negative 1.22, and that's going to give us the concentration of hydroxide ion. Okay. All right, so in this, the charts are all goofed up. That shouldn't be here, and that also, I don't know why it's there. But let's just go with it. How do we measure pH in a lab? Well, we use two ways. One way is to use litmus paper, which is a good way. I mean, if you want to know if something is definitely acidic or definitely basic, and you want to get a guesstimate as to where the pH falls, litmus paper is pretty good. Okay, it's going to be quick and easy, painless, boom. If you really want to get more specific as to what the pH of something is, you could use a pH meter. Okay, where you take a glass probe, stick it in solution, and it's going to measure the pH of your solution. Okay, now you can also determine the approximate pH of a solution by using something called an acid-base indicator, which is a substance that changes color in a specific pH. Okay, so the way this would work is, let's say you have an indicator, you have an acidic form of the indicator, which I'm going to shorthand indicator with IN, and then we're going to protonate that so it's the acid form. Okay, so it's going to have a certain color as an acid. We react that with water, and the two products are going to be H3O plus, because that water picks up the proton, and then you're going to have the indicator ion. And this ion minus, this is actually your base color. So usually an indicator is going to have one color when it's predominantly in the acidic form, and then another color when it's predominantly in the basic color. Okay. So if we're going to define this in terms of the equilibrium of an indicator, okay, the equilibrium constant of the indicator is going to be equal to the concentration of H3O plus times the concentration of the indicator ion divided by the acidic form of the indicator. Okay? All right. So at this point, if I wanted to get a ratio of the indicator by itself, okay, let's say I want to get the indicator by itself, I'd have to multiply both sides by the concentration of the acid indicator. So that would be the equilibrium constant times the concentration of acid. That's going to be equal to the concentration of H3O plus times the base indicator. Okay? So now what I'm going to do is divide both sides by the indicator ion. Okay? And so we're going to get this the equilibrium constant times the concentration of the acid indicator divided by the concentration of the base indicator is equal to H3O plus. Now, ideally, we want to get a ratio of the acid indicator to the base indicator. So if we divide both sides by the equilibrium constant, okay, we're going to get something like this, where the concentration of the acidic form divided by the basic form of the indicator, this is going to be equal to the concentration of H3O plus divided by the equilibrium constant of the indicator. So what this is telling us is that if the concentration of H3O plus is greater than the indicator, so if this one is higher than the indicator, are we dealing with more acidic, or are we dealing with a more basic solution? Well, it would definitely be acidic. Okay. Now, if your eye needs a 10% or 10 times difference in concentration to see the color, what is the pH range of this difference? Basically, we need to see, in order to see a color change, we need to see a pH unit every time there's a color change. So every time there's like a shade difference in color, that's usually going up or down a pH unit. Okay, and so the picture that is showing up here, this is a chart of some of the more common acid-base indicators. The most important one, or the most widely used one, is phenolphthalein, because in phenolphthalein, in the acidic form, it's completely colorless, but once you start getting to that point where you start crossing over, it turns a dark red color. Okay, so phenolphthalein is the universal indicator. That's the one that's used a whole lot. Bromothymol blue is also used quite a bit. It starts off yellow in the acidic form, but then turns a really nice dark blue when you get a little bit basic. Thymol blue is also a good one, but it has a very short pH range, and also it's going to turn red. It's going to turn red when it's very, very, very acidic, and it's going to turn yellow, even though it's still in that acid range. And then finally, it's actually going to have two. When you get into more basic ranges, the yellow turns into a blue. Okay. But so we could definitely use an acid-based indicator in order to help us determine colorimetrically what is going on, where are we at in the titration.